Okay, take two. Lesson 5, last lesson of the chapter, we're talking about radioactive elements. Now, this is not a new concept. We've talked about radioactivity before. Think back to when we were talking about earth science and decay and dating things. We've also talked about isotopes in lesson 1. So most of this should make sense. Some of it will be new. So, radioactivity, defining what it is. This is the process, right, of what happens when radiation is emitted from an element. So you have some sort of atom, and for some reason, it's emitting radiation. That can take place when there's a reaction that changes the nucleus of an atom. That can also take place in radioactive decay, but radioactivity is the process where radiation is emitted. Radiation is the actual energy in the form of rays or particles. So radiation is the energy, radioactivity is the process of emitting that energy. Oh, struggled there. So then we have different types of radiation that we'll talk about. We mentioned before that an atom can be changed in its number of electrons, and we call that an ion. You can change the number of neutrons, and we call that an isotope. A lot of what's going to be happening here is changing the nucleus of an atom. And typically, it's going to be because we're changing the amount of neutrons. So atoms that have too many or too few neutrons tend to be unstable. And then they want to go through some sort of process to bring them back to a stable form. That could even be changing into a completely different type of atom. That is where we get radioactive decay. So, radioactive decay, you're emitting radiation in this process. So it's similar to the process of radioactivity because there's radiation being emitted, but here you're actually decaying an atom and it's going to form a different atom. There are three main types of radiation that we're going to be talking about: alpha, beta, and gamma. So the first is alpha, and there's a lot here, but just follow along with me. So alpha radiation is made up of positively charged particles called alpha particles. Now, they're positively charged and they do not have an electron. Basically, they're the same as the nucleus of a helium atom. So there are two protons and two neutrons. That's why sometimes you will see this as opposed to the alpha symbol that you see there where it shows the alpha particle. Sometimes they'll have a helium atom with the 4 and the 2, because remember, that's how you write isotopes, to show that it's an alpha particle. And so if you were to write the nuclear equation showing the decay of radium, right? So you have radium and it's going to decay by alpha radiation. That means that there's going to be a loss of 4 at the top and 2 at the bottom. Remembering the number at the top is the mass, the number at the bottom is your number of protons. So if we lost 2 protons and 2 neutrons, that's losing a mass of 4. So we went from 226 to 222. And that 2 at the bottom represents the protons, so we're losing 2 protons, so we're going from 88 to 86. Now, I told you that you went from radium to radon, but in the event that you just knew that radium was undergoing alpha decay and you didn't know what the result was going to be, you could use a periodic table. So you know that alpha decay is 4 and 2. So subtract 4 from the top, subtract 2 from the bottom, and remember, you identified an element based on the number of protons. So the number of protons would have been 86. Look for element 86 on your periodic table, you would have gotten radon. Okay, so beta radiation has a negative charge, and it emits beta particles. So this is the beta symbol. Sometimes you will see it represented as an E with a 0 and a 1. And basically what happens here is you have a neutron that's converted into a proton and an electron, but that electron is emitted, so pretty much you're just left with the proton. And so there's not going to be a change in the mass because remember, you have a neutron turning into a proton. They have the same mass. So even though now you have more protons than you have neutrons, the mass is the same. But that bottom number is going to change because now you have one extra proton. So if you look at the equation here, the carbon, it stays carbon 14 to nitrogen 14 because you didn't change any mass, but you added an extra proton, so that 6 becomes a 7. So then we have gamma radiation, and gamma radiation is very high energy. It's neutral though, and there's no mass. What that means is it has no charge and it adds no mass, but a lot of the energy lost during radioactive decay comes from these. And it's usually going to be accompanied with an alpha or a beta. So if you look at this equation here, the uranium underwent gamma and alpha radiation. But when you look at the change, the new atom is thorium, and you see that it just lost 4 at the top and lost 2. So it was the alpha particle that made the change. The gamma ray didn't change the mass at all. So this is just a little illustration that shows you the charges of each one of those. The beta particle is going to have a charge of -1, so it's going to be attracted more to the positive plate. The alpha particles are going to have a charge of +2, so it's going to be more attracted to the negative plate. And the gamma rays are neutral, so it'll go straight down. So then half-life. We've seen this before when we were talking about like carbon and radioactive dating and things like that. So remember, half-life is the amount of time it takes for a nucleus, basically of an isotope, to decay by half. So if you had uranium and you wanted to see how long it took for it to decay exactly half of the nucleus that it has right now, that amount of time is the half-life. The original radioactive nucleus is called the parent nucleus, and what's left over after you have your stable atom is your daughter nucleus. So we've mentioned this process before of nuclear fission and nuclear fusion when we were talking about energy. Remember, nuclear fission is the process of breaking apart nuclei and releasing energy. So here you have an example, and this diagram is in your book as well. You have uranium, and you're splitting it, and you have 2 different atoms now, barium and krypton, and 3 neutrons. You lose a lot of energy as well. So even if you were to put those neutrons and that krypton and that barium back together, you would have a lot less mass than that original uranium because you lost a lot of it due to energy. Then we have nuclear fusion. And remember, nuclear fusion is the whole ITER project that they're trying to do, right? Basically building stars, fusing together small nuclei into a larger nucleus. But you need extremely high temperature and pressure to do this. And so the issue here is finding an environment on Earth that can sustain this and replicate this type of environment to do this. So there's benefits to nuclear fusion and fission. The main thing with fission is people think that there's a lot of waste accompanied with it, which there is, but there's lots of things that people are trying to do right now to reduce some of that nuclear waste. But nuclear fusion is what people believe is going to be the energy of the future. So we'll see. That is the end of lesson 5 and the end of chapter 12.